Okay, so in the last class, we discussed, we just started the topic of 2's complement number system. So, it might be a good idea to again start from there. Okay. As I told in the last class, 2's complement number system is not just 2's complementation. You are all familiar with 2's complementation, that is complement each bit of a binary word and add a 1 at the LSB, then you get 2's complement, which you can use in some context as the negative of that number. Okay, but that is different. 2's complement number system is a system. Okay. Now, before I get into this, let me set certain things in the beginning. Suppose A is there, A is a variable and it is a binary variable. In binary domain, it can take binary 1 or binary 0. When it is in binary domain, then it follows binary arithmetic, that is 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 1 is 0 with carry 1 and all that. In binary domain, we have only these operations. We cannot have minus 1 or 1 binary 1 into some decimal 5. This has no meaning. So, when you do in the binary domain, we take A as binary 1 or binary 0 and follow normal binary operations, that as I told you just now, complementation, addition, etc. But same A, when I take it in the decimal domain, then if A is binary 1 here, I will take it as decimal 1, and if it is binary 0, I will take it as decimal 0. In decimal domain, if I am evaluating something, there I can use decimal operations, for instance 1 into 5, 1 into 6, because they are decimal numbers, minus 1 and things like that. Okay. So, depending on which domain I am in, A will be treated as a binary variable, take value 1 0, or decimal variable again say similar 1 0, but here I can use decimal arithmetic operations, here I can use only binary arithmetic operations, okay, on the same A. We will have to make these distinctions in all what we do, because in our in all the systems we discuss, the same variable A will be originally binary variable, but we will also take it in the decimal domain, that time it will be viewed like this. Okay. We are given a x, this is the most significant bit x w minus 1, then x w minus 2 dot 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 x w minus j minus 1 dot 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 x 1 x 0, and there is a binary point. The binary point is not hardware, it is in our mind. I mean, if you want, you may not put it here, you may put it at the end, then it will be an integer, but normally we prefer fractional numbers, we put it here, its actual meaning will come now, but it is again in your mind, it is just a point of reference and nothing else. Okay. Now, such, and here every variable, whether x w minus 1 or x w minus 2 or this or x 1 or x 0, every variable is a binary variable, that is every x w minus j minus 1 binary. J can be 0, then you are here, j can be 1, so w minus 2 you are here dot dot dot, if j is w minus 1 you are here, total w, but for all of them this variable is binary. Okay. So, either binary 0, binary 1, and when I am writing the word, in this word they will follow the binary arithmetic, because they will be treated as a binary variable. So far so good, but under 2's complement system, if I give you this word, w bit word, what is its decimal value? That is what defines the 2's complement number system. Under 2's complement number system, it has a decimal value, this d for decimal. So, x has a decimal value, and this time I will write an expression which will be a decimal expression. So, I will use the same variables in this expression, but now they will be viewed as decimal variables, not binary variables, though they will still take 1 or 0, but I will take them as by decimal 1, decimal 0 in this expression that I am going to write. And then since it is a decimal expression, I can jolly well use minus sign, into 2, into 4, like that. So, this decimal expression will be minus x w minus 1. So, now x w minus 1 here it was a binary variable, binary 1 or binary 0. If it is binary 1, in this expression it will be decimal 1. This is a convention. If it is binary 0 here, it will be decimal 0. And now minus decimal 1 minus decimal 0 is okay. Decimal arithmetic permits minus sign. The next one is this. Now plus will start coming. This into first negative power, 2 inverse. Then dot dot dot. This will be 2 to the power minus j. You can see easily it will be 2 to the power minus j, because if it is w minus 1, there is no 2 to the power, there is 2 to the power 0. So, if it is 1, it is 0. Then if it is 2, w minus 2, it is 2 to the power minus 1. So, if it is 2, 1 coming here. So, if it is j plus 1, it will be in the bracket, it will be j here. Going that way, and last one is this. All right. Okay. Now, let us see, this is a decimal expression. Let us try to understand its meaning. Suppose this fellow is 0, MSB is 0. If it is 0, then obviously this is a positive number, because minus 0 is 0 and all other fellows are positive. So, it is a positive number. Okay. In that case, minimum will be when this is 0, this is 0, this is 0, this all are 0, only x 0 is 1. So, it will start at this value 2 to the power when all are 0, only x 0 is 1. The next will be x 1 1, x 0 0, all right. So, that time it will be 1 here. So, 2 to the power all right here, there will be 1 1. So, it will be summation of the 2, so on and so forth. So, you can see that at every step as I go on increasing from all 0, then 1 here, then 1 0, then 1 1, number value is increasing by this step 2 to the power minus 1. Well, what is this? After all, it is twice this. Okay. Then if it is 1 1, if it is 1 1 means it will be so it is thrice this. Okay. So, like that. So, if it is all 0 but 1 here, it will be just this much. If it is all 0 but 1 and 0 here, it will be twice this. If it is all 0 but 1 1 here, it will be thrice this. So, this is the basic unit by which it keeps increasing. So, finally, it will increase maximally up to what? When MSB, there is most significant bit is 0, but all the other fellows are 1. That is the highest positive number. So, highest positive number will be as per this formula minus 0, which is 0, then 1 into 2 inverse, that means x d, its max will be equal to 2 inverse, then 2 inverse 2 dot 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 2 inverse w minus 1, sorry, w minus 2 plus 2 inverse w minus 1. In the last class I have shown, so it is basically GP series, you can take out 2 inverse out, so it will be 1 plus 2 inverse plus 2 inverse 2 and dot 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 dot. So, it is a GP series, you can take the sum of a GP series. Okay. Alternatively, the way I do, I add this like this, this I add here and subtract the same thing. So, if you add them, these two, if you add is twice of this, so you get here, and if you add this, you move here, and like that, so and so forth. So, finally, twice of this will come, which is 1, and you are left with this minus. Okay. This is my way of doing, but you can carry out a GP sum series, GP series sum, and you will get the same thing. So, this is what you have. Okay. You are starting at 2 to the power minus w minus 1, then twice that, thrice that, 4 times that. Finally, you are here. This is the maximum you can get. If w is large, then 2 to the power minus bracket w minus 1 will be very small. So, it will be approximately equal to 1, but theoretically it is less than equal to 1, less than 1 always. So, it will not exceed 1 under this system if I imagine a binary point here. Okay. So, it will be less than 1, which means when it is positive at least it is a fraction, it is less than 1 between 0 to 1, very good. Now, we go for the other side. If this fellow is 1, earlier I took the MSB this to be 0 and I found the number to be having positive decimal value, and we started going up from 2 to the power minus w minus 1, then twice that, thrice that, 4 times that, dot 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 up to this. This comes when all the fellows are 1 and the MSB is 0. This part we have covered. Now, suppose the MSB is 1, suppose is 1, then I have minus 1 here, minus 1. If now all the other fellows are zeros, then from all the positive there is no contribution, because 0 here, 0 here, 0 here. So, we have got maximally negative value. So, if it is 1.00000, it will have a binary value, a decimal value equal to minus 1. Minus 1 plus 0 times something, 0 times something, so it is 0. Then if you go up slowly 1.00 dot 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 1, that means it will be minus 1 plus only this last fellow, because 1 is there, others are zeros. So, this. So, from minus 1 we go up in the upward direction by this much. If it is 1.00 dot 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 10, it will be minus 1 plus 1 here, 0 here. So, this is twice, 2 times this basic quantity, and so on and so forth. So, from minus 1 it starts going up in steps up 2 to the power minus w minus 1. Okay. As I go along, 1.000 maximally negative, then 0.001 slightly less negative, 0.00010 further less negative, and so on and so forth. It will be 1.00011. So, I am going up in steps up 2 to the power this, in steps up this, 1 times this, 2 times this, 3 times this, like that. Finally, a situation will come when you will have 1.11111. That we will have here decimal value will be minus 1 and then 1 into 2 inverse, then 2 inverse 2 and dot 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 dot, all are 1. So, 2 to the power minus minus 2 minus 1. But these sum I have already worked out a while ago, this is GP series, its value is 1 minus 2 to the power minus w minus 1. So, together it will be minus 1 plus 1, so they cancel, minus this, which means if it is decimal 0 and is minus 0 and minus 1, this is minus 1, then you go up, this is minus 1, this is minus 1 plus 2 to the power minus w minus 1, so this is minus 1 plus twice 2 to the power minus w minus 1 and dot 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 dot. Finally, we are here. So, this much is minus, then if you add next number at 0 point all 0, so you are here, then 0 point all 0 and 1. So, you then go to the positive side, it will be just 2 to the power, then 0 point all 0 1 0, it will be twice this. Dot 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 dot, finally, when it is 0.1111 all ones, you will have the last one 1 minus this. So, this is how it goes. Okay. This is the flow of the 2's complement number system. This is the definition. That under 2's complement number system, if I give you a binary word, it has a specific decimal value given by that formula. Okay. Now, there is an interesting property which we should discuss now. Suppose you are given this binary word, This is a binary word, W bit binary word given to me. We know its decimal value. Suppose I play a game. What I do is I form a number, binary number, maybe x prime, by taking complement of each. This is, if it is binary 1, I take it binary 0. If it is binary 0, I take it binary 1. So, complement. Here also complement. So, I just take complement of each bit. And then I add this number, binary number 0.00000, just 1. That is actually decimally it is 2 to the power minus this. And the resulting number, if I call it y, it will be y w minus 1 dot y w minus 2 dot 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 y. So, if I am adding the 2, all right. Question is, what is this y? That is the thing we will evaluate. But before that, let us examine some basic thing. Suppose there is a binary variable a, binary domain and decimal domain. It can either be 0 or 1. Okay. Then a bar, if a is 0, then I know what will be a bar. A is 0 1 and here it is 0 1, no problem. If a is 0 in binary, it is to be treated as a decimal bit 0. When it is in decimal domain, we do not call it bit anymore, because in decimal case, even if only single point, it can have more than 2 possibility, 0 1 2 3 up to 9. So, whenever you have more than 2 possibility, we no longer can call it bit, we call it a digit. So, it is a digit, but digit value remains same. If it is binary 0, it is decimal 0. If it is binary 1, decimal 1, that is for a. But if it is a bar, if a is 0, a bar is 1. If a is 1, it is 0. And obviously, decimal also it will be 1, because if the binary value has binary value 1, when I am treating as a decimal value, its weight will not change, it will be 1, it will be 0. But you see, I can, my claim is I can write a bar as a bar in decimal. If you want, more clarity, I can write a bar in decimal, that is a bar here. A bar in decimal is 1, decimal 1 minus a by in d. That is a bar, see this value. When a is 0, binary, then in decimal it is also 0. So, if you put that, then 1 minus 0 is 1. So, if a is decimal 0, a bar is decimal 1, 1 minus 0. If a is binary 1, in decimal domain it is decimal 1. If it is decimal 1, then what happens to a bar decimal? A bar in decimal will be 1 minus, by this formula, 1 minus 1, and that is 0, and so you are getting 0. So, this is verified, right? If a is decimal binary 0 and therefore decimal 0, a bar is 1 minus 0, which is 1, so satisfied. If a is binary 1 and therefore decimal 1, then a bar by this formula is 1 minus 1, because a in decimal is 1. So, 1 minus 1, which is decimal 0, satisfied. So, in decimal domain, any a bar will be 1 minus a in decimal domain. That is 1 minus a was originally a binary variable, but when I write an expression 1 minus a, you do not have to always write a by d to indicate it is in decimal. If you simply write 1 minus a, because we are using minus sign, it is automatically implied we are dealing with a as a decimal number. So, if it was binary 1, it will be decimal 1. If it was binary 0, decimal 0, because its value will not change, but domain changes. Domain is decimal, so I can put a minus, I can do all these things. And now it is very clear, if a was originally binary 0 and therefore decimal 0, by this formula 1 minus decimal 0 is 1, okay, which is decimal 1, and a bar should be decimal 1. So, this is matching. Similarly, if a was binary 1 and therefore decimal 1, by this formula 1 minus 1 is 0. So, a bar by this formula is 0 in decimal domain, and that is matching. A bar should be 0 and I am getting 0. So, that means any complement will be 1 minus the original in decimal domain. So, if I add the two, it will be decimal value of this and decimal value of this. Okay. Decimal value of this is minus 0, because it is a 2's complement system. So, minus 0 plus 0 into 2 to the power minus 1 plus 0 into 2 to the power minus 2 dot 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 dot, nothing, only this 1. So, 1 into 2 to the power minus w minus 1. Okay. And here, so I have got, let me write this term, this coming from here, and from here under 2's complement it will be minus of this bit, okay. But this will be 1, like I told you, a bar is 1 minus a. So, in decimal domain x w minus 1 bar, that means if it is binary 0 and therefore decimal 0, in decimal domain this with bar it will be 1 and vice versa. So, there is nothing but 1 minus decimal x w minus 1. Okay, that is this bit, minus because in the 2's complement formula, for I mean the decimal value of a 2's complement number means this has to be treated as a decimal digit with a minus sign. So, minus sign decimal digit. The moment it is decimal, it is 1 minus decimal of this, that is what is coming. Then plus this into 2 to the power minus 1, but this again to be treated as a decimal digit. The moment it is decimal digit means 1 minus this original in decimal form. Sorry, it is 1. All right. This is the total value. This is y decimal. Now, let us try to find out what this is. You take out the minus 1 and then plus 1 into 2 inverse plus 1 into 2 to the power this under one bracket. So, it will be minus 1 plus 2 inverse 2 dot 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 2 inverse w minus 1, and then minus x w minus 1. I have taken a minus out. So, this minus is gone out. So, it will be plus now. Okay. And lastly, this 2 to the power now. How much is this? This summation we have worked out 1 minus 2 to the power this. So, this is minus 1 plus 1 minus 2 to the power minus w minus 1. This part is for this. Then you can see this, sorry, not the minus sign. What is this bracketed quantity? It is nothing but the decimal value of the original number x, this one. There is minus of x w minus 1 and all those things. Okay. And lastly, we are left with this single quantity, this. So, you can see this 1 and minus 1 cancels, these 2 cancels, you are left with this much, which means if you really follow the procedure that you complement each bit of x, add a 1 at the LSB and get a new word, the decimal value of that word under this 2's complement system will be nothing but negative of the original decimal value minus x by d. This is the advantage of 2's complement number system, that is, if you want to take a negation, if you want to do subtraction, you do not need to design a subtractor. You take complement of each bit at a 1 at del SB, the resulting word will have decimal value equal to minus of the original decimal value. So, you just simply add with whatever numbers that will amount to subtraction. Okay. These are main advantage of 2's complement number system. There are some other advantages also. There is a fundamental advantage which I will tell later in the next class, next section. Okay. There is one more property. This is also very, very useful in practice. Suppose x is given to you as a 2's complement number. So, I know what is x by d. Suppose this decimal value I want to divide by 2, that is I want to multiply by 2 inverse. This decimal value I want to divide by 2 or equivalently multiply 2 inverse. Right hand side if I multiply 2 inverse, it will be minus half, first minus half times this. Minus half I can write as minus 1 plus half. It will be minus half times this, and minus half is nothing but minus of 1 then plus half. If I do that, so minus 1 times this will be this, and plus half, that is 2 inverse times, and then 2 inverse times this, it will become 2 inverse 2 times dot dot dot. This will be 2 inverse j plus 1 dot dot dot. This will be x 1 to the power minus and then x 0. Now, if you look at this is the decimal value of a under 2's complement system of this word MSB point. So, that in the decimal domain, when I take the decimal value, minus of this comes, which is present. Next bit is what is associated with the power 2 inverse next, but that is this. So, next will be the one associated with 2 inverse 2, that is this. So, x like that. Finally, x 1 is coming with 2 to the power minus w minus 1, and then x 0 to the power minus w, and then x 0 here. So, size has gone up because this has got repeated. So, earlier size was w, now it is w plus 1. This is the word whose decimal value is this under 2's complement system. What is this word? Original word was this was the original word, w bit word. What has happened? This got shifted to the right by 1, 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 and this is what is called sign bit. Why it is sign bit? I forgot to mention. If this bit is 0, I know the number is positive, and we have also said if this bit is 1, whatever these bits values this bit take, now total number is negative, it is below 0. That is why it is an indicator of whether the number is positive or negative. If it is 0, it is positive, the whole number is positive. If it is 1, whole number is negative, that is why it is called sign bit. So, sign bit also comes here, sign bit comes, the other bits come here, and the same thing gets repeated here. It is called sign bit extension, sign extension. And it is w plus 1 bit. Now, most often we have a finite size register may be w bit. So, in that case, this part will be truncated out, it will just go out because we will take the higher ones. So, this is what we will get. all right. So, if I multiply by 2 inverse, every bit gets shifted to the right by 1, LSB, the least significant bit, gets out, and the sign bit then comes back here as an extension. If I now multiply by another 2 inverse, there is overall 2 inverse 2, then it will be, this will come as it is, sorry. So, this is the word. So, this will get shifted. So, x w minus 1, let me do it here only. This was the word. When I multiply by 2 inverse, another 2 inverse, again same thing, this will be shifted. So, this will come here x w minus 1, next x w minus 1, that will come to this position, and dot 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 x 1 will go out and x 2 will come here, and this will get extended here. So, you see sign bit actually gets extended twice. If you compare with this word, original one, and this one, sign bit got shifted twice, all other bits got shifted twice, and the sign bit got extended once, extended next time twice. So, if it is 2 inverse 2, all bits get shifted to the right by twice, lower 2 bits get chucked out, and the sign bit then gets extended once and one more time, so on and so forth. This is called sign extension, and we have to implement this in digital hardware when we carry out multiplications and other circuits. Okay. Thank you very much. I will move to the next section now. Thank you.